Hello, everyone. Welcome to the Learnable Organization channel.
Today
Um,
we're going to be talking about how stars are made in Unit 2, Stars, Galaxies, and Black Holes in our course Astronomy 101.
Please watch through the video, and this is a very interesting video, and you guys are going to learn a lot. So let's get started. So first, let's talk about the life cycle of a star. Well, the life cycle of a star starts from like enormous gas clouds in like nebulas, which will then collapse because of gravity and then turn into the first protostars. And then they'll go on to T-Tauri stars, then main sequence stars, then red giants or supergiant stars, and then finally die and then turn into white dwarfs, neutron stars, black holes. We will get into all of these later on in the video. So let's talk about the first stage, protostars. So a protostar is a very young star that is still in the process of forming. It is in the earliest stage of stellar evolution. Where gathering mass from a parent molecular cloud, this stage can last about 500,000 years for a low mass star like our sun. During this stage, a dense core within a molecular cloud fragment collapses under the force of self-gravity. As the core collapses, it heats up and an opaque pressure-supported core forms inside. The protostar phase ends when an infalling gas is depleted, leaving a pre-main sequence star. This star will then contract and become a main sequence star when hydrogen fusion begins at its core. Now, Sanjay will be talking about the next phase, T-Tauri stars.
T-Tauri stars are a class named after the prototype T-Tauri, a young star in the Taurus-forming region. They're found near molecular clouds and are identified by their optical variability and strong chromospheric lines. T-Tauri stars are pre-main sequence stars in the process of contracting to the main sequence along the Hayashi track, a luminosity-temperature relationship obeyed by the infant stars of less than 3 solar masses in the pre-main sequence phase of the stellar evolution. Next, Manus will be talking about nuclear fusion.
So let's talk about how the stars can be made. So stars are made in the cloud of gas and dust called stellar nebulas. An example is the Orion Nebula. Disturbances inside the cloud caused by turbulence cause high-density areas called knots. These knots have enough mass that the gas and dust inside collapse due to gravity. But due to pressure from the gravity, the center mass starts to heat up and creating the first type protostar. After enough time, the core gets hot enough to start fusion, making it a star. The knots can also collapse due to gravity in multiple areas, making two or more stars, in the process causing a multi-star system, such as a binary star system. These stars also rotate around each other due to their velocity, spin, and gravity. A star's lifespan depends on how big it is and how much it weighs. Usually, the more massive the star is, the faster it dies, while the less massive star is, the longer it survives. The color of the star depends on how hot its surface is. So now let's talk about nuclear fusion. Stars use the process of nuclear fusion with hydrogen forming helium, which causes energy to jump out of the star, which is how sunlight reaches us. It also uses this fusion process to stop gravity from compressing the star, which helps maintain a hydrostatic equilibrium or a balance between a force and gravity and internal pressure called nuclear fusion. So basically, because of the nuclear fusion, it pushes out against gravity, but then gravity pushes in on the star, right? And so when gravity pushes in on the core of the star, the core heats up, and then it causes more pressure on the outside, which stops gravity from making it collapse. And so that is called the hydrostatic equilibrium. And so both forces balance out each other. Now, how a star dies is when the hydrostatic equilibrium, so like the pressure from the fusion, fails, and the gravity will just make the star collapse, which causes it to die. Now, Sanjay will be talking about another step in the nuclear fusion process, the proton chain.
Proton-proton chain is a process that stars use to enable nuclear fusion. In simple terms, it's how nuclear fusion works. When a temperature of 15 million degrees Celsius has been created at the core of a star, nuclear fusion begins to take place. But how? To begin its journey into life, a star starts fusing elements to help keep it running. Firstly, it fuses 4 hydrogen atoms and creates a helium atom, which means all the star does is fuse at high temperatures in the core. It takes the 4 hydrogen atoms and fuses into helium atoms like multiple times, and then eventually it will create a helium core. But we will talk more about this later. And first, we got to talk about low mass stars.
So, low mass stars.
After the T-Tauri phase, there's enough heat in the star's core to start nuclear fusion. At this point, the star's main sequence phase starts. This is the longest period of the star's life, spending most of its time in this stage. During this period, hydrogen is fused in the core, like we said before, for the most part, creating helium in the core as well. The energy created from nuclear fusion counteracts the force of gravity, establishing a long period of hydrostatic equilibrium. It's basically where both the forces are balanced, like Mohammed said. In this stage, the star runs out of most of its fuel and transforms into a red giant. After all the hydrogen fuses into helium, it will turn into carbon, then nitrogen, and so on, oxygen, neon, magnesium, silicon, sulfur, or argon. And then finally, after a few more, it'll reach iron. But these are for high mass stars. For low mass stars, it will only reach until helium in the core. These are elements the sun fuses because it's a low mass star and it will not because the beginning mass of a star depends on how much dust has been received from the nebula. So a low mass star only fuses less elements until helium because there's less pressure, which means that it will only fuse until helium. In the red giant phase, which is the next phase after the main sequence, the star will cool down and get larger since the force of the outward pressure by nuclear fusion is greater than the inward force of gravity. The star will contract and then expand, becoming cooler, and at one point, the core of the star will turn into a white dwarf, while a planetary nebula surrounds it. A planetary nebula is a region of gas and dust where new stars can form. A white dwarf, the remnant of the star, is extremely small, hot, and dense, where the weight of with the weight of 0.17 solar masses to a weight of 1.33 solar masses in a tiny Earth-sized sphere. How is this even possible, though? The intense amount of density is held through the electron degeneracy pressure, where the electrons transform into the lowest energy states and stop the inward force of gravity from making the white dwarf collapse. After a long time, if the white dwarf has less mass than 1.4 solar masses, it will eventually die out and become a black dwarf. Otherwise, it will become a neutron star or a black hole if it's a high mass star. Next, Manu will talk about the CNO cycle.
Now, the CNO cycle is for mainly high mass stars. Okay, so there are many differences though between low mass and high mass stars. High mass stars remains for a significantly short period of time in the main sequence as their main structures cause them to burn their fuel faster. After the proton-proton chain, which fuses hydrogen into helium and helium into carbon, high mass stars will go through the CNO cycle, carbon, nitrogen, oxygen cycle. During this period, the stars fuse through many more elements. In this process, carbon and hydrogen atoms go through fusion and decay processes to create nitrogen, and hydrogen go through the same process to obtain oxygen. This process is unique to the high mass stars from above 1.5 solar masses. The process of nuclear fusion for the heavy stars is extremely fast compared to the low mass stars. After all the hydrogen fuses into helium, it'll turn into carbon, then nitrogen, and so on. Oxygen, neon, magnesium, silicon, sulfur, argon, calcium, titanium, chromium, and iron, finally. These are the elements that the sun fuses from direct fusion, but sometimes during the fusion process, some intermediate products will be created, such as beryllium, boron, and lithium, which will then eventually fuse into carbon. Now, the reason why high mass stars go through their life cycle much quicker than low mass stars is because they are much more heavy, which means that there's more gravity pressure placed at the core of the star, and so the core of the star like heats up even more and causes it to burn its fuel even faster. And so and since they're bigger, they're also much more brighter, and so they burn through their fuel really quickly. Now Sanjay will be talking about high mass stars.
High mass stars have a higher mass, which makes them generate nuclear fusion even faster and hotter, reaching elements until iron. But the high mass stars on the main sequence are also for a shorter amount of time than low mass stars, and after this phase, they reach the supergiant phase of their lives. At this point, they're extremely unstable and begin the CNO cycle that Manit was talking about before. High mass stars have a completely different life than low mass stars. Their life can be compared to a race where high mass stars are participants in the 100-meter dash, while low mass stars are participants of the mile. Both of them run, that is, they can both do nuclear fusion, as low mass stars and high mass stars undergo the proton-proton chain, while high mass stars also do some extra fusion through the CNO cycle, as well as fusing up the iron in its core. Even though these high mass stars fuse more elements than a low mass star, they live a shorter life. Going back to the race analogy, and you will see that the high mass stars use 100% of their effort while running the 100-meter dash, fusing elements of the iron in its core and finishing quicker, while low mass stars use 50% of their effort and only fuse elements of the helium in the core and finishing way after. After that supergiant phase, these high mass stars are likely to change the luminosity as they contract and expand variably as the net force of gravity and outward pressure from the nuclear fusion keep changing. Once this starts, it will become extremely unstable as the force of outward pressure will overpower gravity as nuclear fusion will not be possible anymore. When this happens, the star will instantly collapse on itself and explode into a supernova. The remnant of the star will either be a neutron star or a black hole, depending on the initial mass of the star. Remember, more mass is equal to more fusion, and the heavier it is. So the neutron star is a remnant of the high mass star, which has a smaller size but high density. That has like basically 1 teaspoon of it would weigh billions of tons. The star is composed of neutrons as the protons and electrons combine and created because of the great pressure inside. The star is held together by neutron degeneracy pressure, unlike the white dwarfs, which are held by electron degeneracy pressure. And this is so powerful that it can withhold the density and pressure of these massive stars. Black holes are the second option for a high mass star to form into. These high mass stars must weigh way more than what is needed to create a neutron star, as black holes are remnants of the heaviest high mass stars. Black holes are the most unique objects in the universe. And black holes are objects that have such immensely OP gravitational pulls that even light cannot escape it. Whenever an object or light crosses the event horizon, it cannot escape. And when it reaches the singularity or the center of the black hole, all the information will be sucked in and probably lost forever. Black holes are one of the most interesting objects in the universe, and we will talk about this in one of the next few videos. Next, we'll talk about the nuclear fusion process slides. What is nuclear fusion, and why is it important? First, there's hydrostatic equilibrium. A star reaches that once the force of gravity and the nuclear fusion counterbalance each other, and they stay on the main sequence line. But all stars do this, low mass and high mass stars. Low mass stars go through the proton-proton chain, and they spend most of their time in the main sequence, and they die as white dwarfs. While high mass stars go through the proton-proton chain and the CNO cycle, and they also stay in the main sequence, but they burn out quicker and either die into a neutron star or a black hole, depending on their mass at the beginning of their life. Next, Manu will talk about population 1 stars.
Yeah, and so before we talk about that, real quickly, so the three outcomes for high mass stars are, I mean, for stars when they die, is a white dwarf, a neutron star, and a black hole. Nice interstellar reference right there. Okay, so let's talk about population 1 stars. So population 1 stars are younger and more metal rich. They form the disk of the galaxy. An example of a population 1 star is our sun. Population 1 stars consist of younger stars, clusters, and associations. Basically, stars that formed about 1 million to 1 billion years ago. Certain stars, such as very hot blue white stars, are designed as extreme population 1 objects. All known population 1 members occur in spiral galaxies. They also have been detected in some young irregular galaxies, possibly when two galaxies collide, as mentioned in the previous video. Population 1 stars are the result of multiple stars being born and dying. As a result, such objects contain iron, nickel, carbon, and certain other heavier elements in levels that approximate their abundance in the sun. Like the sun, however, they must consist mostly of hydrogen, about 90%, and helium, up to 9%. Now let's talk about population 2 stars. Population 2 stars found in the bulge and halo of galaxies are the next generation of stars and very metal-poor stars, but can form such as elements such as carbon, oxygen, calcium, and iron. Population 2 stars consist of the oldest observed stars and clusters, which formed about 1 billion to 15 billion years ago. These stellar objects are relatively rich in hydrogen and helium, but poor in elements heavier than helium, containing 10 to 100 times less of these elements than population 1 stars. Because such heavier elements had not been created in large quantities at the time of their formation. Large numbers of these objects also occur in elliptical galaxies. Now let's talk about population 3 stars. Population 3 stars are hypothetical stars that are the oldest of all stars. They're supposed to be extremely massive, luminous, and hot stars that have very little amounts to no metal, very little amount to literally no metal inside of the star. This is because they were supposedly made just 100 million years after the Big Bang, which was 13.7 billion years ago. And at that point, there was no metal existing because stars didn't have enough time to fuse it. The existence of this type of star is inferred from physical astronomy. Now let's talk about the age classification of stars. So there is the protostar, which is the youngest. Then we go to main sequence stars, which is the big chunk of their lives. And then we go to end of the life stars. Okay, so this could be giants, supergiants, or even hypergiants. And then we go to stellar remnants, which is basically once a star dies, which could be black holes, neutron stars, or white dwarfs, as previously mentioned in the video. So now let's talk about main sequence stars. So the first type of main sequence star is a blue color star, which is the O class type of star. So these stars are categorized by temperature and also by color. So let's get started. So blue type O class stars. So these are the hottest stars with temperatures ranging from 30,000 to 60,000 Kelvin. They're also much larger, 12 to 25 solar diameters, and more massive, 20 to 100 solar masses than compared to the sun. And by the way, one solar mass is the weight of our sun, and one solar diameter is the diameter of our sun. So yeah. Examples of O-class stars include Rigel, Spica, Betelgeuse, which might explode as a supernova in our lifetime. So be a pretty cool sight. So yeah, and so blue giant stars, blue supergiants, and blue hypergiants are usually categorized as O-class stars. So now B-class stars. So these stars have temperatures ranging from 10,000 to 30,000 Kelvin. They are also extremely luminous and blue color. And so blue giant stars are usually in this category. Then comes A-class stars, which are in white color. These stars have temperatures ranging from 7,400 Kelvin to 10,000 Kelvin. Lines of hydrogen are prominent in their spectra. Blue giants are also usually in this class. Then comes yellow and white stars. So these are F-class stars. These stars have temperatures ranging from 6,000 to 7,500 Kelvin. They're still hotter than the sun, but not as hot as blue or white stars. So yellow white stars are usually like yellow subgiant stars. And then comes yellow stars. So these stars have temperatures around 6,000 Kelvin. Our sun is a G-class star, which is a yellow star. And so another example is Proxima, yellow dwarf star. So yellow dwarf stars are like right in that middle between the hot and like cool stars. So our sun is right in the middle of the classification of stars. And then comes orange K-class stars. These stars have temperatures around 4,000 Kelvin, and they are cooler than the sun and smaller in size. And so examples of this could be an orange dwarf star. And then finally comes red or M-class stars. These are the coolest types of stars, temperatures less than 33,500 Kelvin. They are also smaller in size, only 0.1 to 0.6 solar diameters, and less massive, 0.08 to 0.5 solar masses than the sun. Examples of these stars could be red dwarf stars. So red dwarf stars are stars which are in the stable phase of their life, and so in the middle. So right between protostars / T-Tauri stars and end of the life stars. It's like supergiants and whatnot. So now let's talk about end of life stars. Stars can start off at any type of size, and so they could go from red dwarf to orange dwarf to yellow dwarf. They could be blue supergiants, blue hypergiants. So they can start off at any type of size or classification. But as they reach the end of their life, red dwarfs, orange dwarfs, yellow dwarfs, and blue giant stars will all turn into red giant stars as their hydrogen fuel runs out. Blue supergiants will turn into red supergiants, and blue hypergiants will turn into a red hypergiant. Red supergiant stars have K and M spectral types. They're about 10 to 40 times more massive than the sun, with surface temperatures ranging of 3,500 to 4,500 Kelvin. Though they are much bigger, red supergiant stars are much cooler than our sun. Red supergiants are typically several hundred to over 1,000 times the radius of the sun. Red giants are also cooler than our sun, with the temperatures ranging from 2,200 to 3,200 degrees Celsius. They can grow to be 100 to 1,000 times hotter than our sun. Red hypergiants are also cool stars. They are among the largest known stars and have M-type spectra. And so next, so we have stellar remnants, and so they can be black holes, white dwarfs, or neutron stars. So now let's talk about size classification. Now, size classification and age classification are related, but size classification is different. So red dwarf stars are small. They are cool main sequence stars with spectral type M. They range in mass from about 0.08 to 0.5 solar masses and have surface temperatures less than 4,000 Kelvin. Then comes the orange dwarf star, which are main sequence stars with spectral type K. They're cooler than the sun and smaller in size. Yellow dwarfs are main sequence stars with spectral type G, like our sun. They have masses similar to our sun and surface temperatures around 6,000 Kelvin. Yellow subgiants are stars that have evolved off the main sequence or are in the process of becoming the giants. So they're right between the dwarf and giant phase. They have exhausted the hydrogen in their core and are expanding and cooling. Blue giants are large, hot, luminous stars with spectral type O or B. They are larger than the sun, but smaller than the red supergiant with surface temperatures of 10,000 to 50,000 Kelvin. Blue supergiants are hot, luminous stars of spectral type O or B. They are less luminous than the blue hypergiants, but more luminous than blue giants. And then blue hypergiants, well, they're very rare, extremely luminous stars with high mass loss due to their extreme solar winds, and they have spectral type O. Now, Sanya will be talking about another classification of stars, which is the luminosity scale.
So, like Mohammed said, another way to classify stars is by the luminosity class, which is based on the star's size and brightness. The luminosity classes are 1. Supergiants, 2. Bright giants, 3. Giants, 4. Subgiants, and 5. Main sequence stars or dwarfs. Next up, we'll be talking about brown dwarfs. A brown dwarf is an astronomical object that is intermediate between a planet and a star. Brown dwarfs are sometimes referred to as failed stars because they have more mass than planets, but not enough mass to sustain nuclear fusion of ordinary hydrogen in their cores, unlike main sequence stars. Brown dwarfs usually have a mass less than 0.075 times that of our Sun, or roughly 75 times that of Jupiter. This maximum mass is a little higher for objects with fewer heavy elements than the Sun. Brown dwarfs are not actually brown in color, but can appear from deep red to magenta, depending on the temperature. The surface temperature of brown dwarfs depend on their mass and their age, just like stars. The most massive and youngest brown dwarfs can have temperatures just as high as 2,800 Kelvin, while the oldest and smallest can be as cool as about 300 Kelvin. L-type and T-type stars are brown dwarf stars. L-type stars range in temperatures from 1,300 Kelvin to 2,000 Kelvin and are usually purplish red in color. And T-type stars have temperature between 700 Kelvin and 1,300 Kelvin and are of a brown red hue. So thank you for watching today's video. It's been really fun.
Yeah, thank you all for sticking around. This was a long video. Hope you guys enjoyed it, and I told you guys it was interesting, right? So, yeah. So thank you for watching.
Don't remember